Yes, it is recording. Yeah. Okay, so let me just share my screen. Yeah, my screen is visible, right? I hope so. So, okay, I already have this open. Chapter 6. Anyway, I might not need this. Chapter 9.1. Right. So I'm just really I'm going to rediscuss this power function thing, and I'll just dive into some problems from 9.1 itself before moving on to 9.2, just so that the concept of the power function is really clear to everyone. So again, so power function is just really it's just a probability thing, right? So it's just you plug in different values of your parameter, and what you get outside are the uh, different values of rejecting your null hypothesis. So don't know what heading to give. Anyway, so power function. Oh, okay. So power function. Power function. Right. So again, so power function is often denoted by this pi of whatever your parameter is, let's say theta, given your test procedure, which is delta, and this is nothing but just the probability of rejecting your null hypothesis. That is all that is. It's a simple probability thing, right? And what does this notation really means is that um, you change, you put in different values of theta here, theta whatever, and given so you fix your criteria to reject your h naught, and then you try out different values of theta, and you will get different probabilities of rejecting h naught, right? So and what is delta? Delta is just some rule that, let's say, reject h naught if, let's say, the observed sample mean is greater than some c, right? So that is just what power function is. It's just a rule. uh, Sorry, that is what delta is. It's just a rule ki agar if I go out there, if I collect a sample, I calculate the sample mean, and if that sample mean is greater than some value, that value is often decided by us only, then I'll reject my h naught. That is what delta is. There is really nothing else. Now, what is rejecting h naught? Now, okay, so this is kind of incomplete. So, right. So again, if you guys have any doubt at any point, just interrupt me. Right now, the thing is, when we reject h naught, right? When we are trying to calculate the probability of rejecting h naught, we are calculating a probability, right? And we cannot calculate the probability without assuming some parameter. And this is going to be clear when we do a example. But I'm just talking about the concept that we cannot, I mean, calculate or write that expression without assuming theta to be something. So when I write this in probability terms, I so this is basically what is, so this basically says ki if my parameters value is theta, right? If my parameters value is theta, and this is my test procedure, then what is the probability of rejecting h naught? So if that is in this notation, you would just write this as probability of rejecting h naught if your parameter value is theta, and that is just what power function is. Now using this power function we can define your level of significance, right? So level of significance, and level of significance is just what's your uh, level of significance is in words. In words it is just maximum probability of type 1 error. That is your level of significance. In words it is just the maximum probability of you making a type 1 error if you follow some test procedure, right? That is what level of significance is. Now how do we rewrite this in terms of power function? Well, uh, I mean a quick reminder ki this is how we write our null hypothesis. Our null hypothesis is if the parameter belongs to some set, some particular set, let's say omega naught, or alternatively it doesn't belongs to that set and it belongs to some different set, let's say omega 1. And what was probability, what was type 1 error? Type 1 error was rejecting H naught when H naught is correct. So that is what type 1 error is. Now what is the probability of rejecting or what is the probability of making a type 1 error? The probability of making a type 1 error would be, you know, when our rejection criteria is fulfilled, right? So we reject everything, or we reject our H naught if our xn bar, or xn bar is specific, let's say our theta, whatever, or whatever sample counterpart of theta. So see, theta is the parameter, right? So we can't observe the parameter. To say something about the parameter, we use some sample counterpart of the parameter, right? So let's call that sample counterpart to be theta observed. Now our test rule says that if theta observed is greater than some c, then we reject H naught. So what is my type 1 error would be? It would be probability of rejecting H naught when my H naught is correct, right? So just a sec, this is so when H naught is correct, so when H naught is correct, what does that mean? It means that theta belongs to this omega naught, right? So what is the probability of rejecting H naught when theta belongs to this omega naught? And see, so now theta here can have so let's say if your omega naught is some interval, let's say 0 comma 1, right? Then saying that theta belongs to omega naught is essentially saying that theta belongs to this interval 0 comma 1, which means that theta can take any value between 0 and 1, right? So this expression right here would have multiple values according to what exact value this theta takes, right? So if theta is 0, then the probability of rejecting H naught given theta is 0 would be different than if theta is equals to 1, or let's say theta is equals to 0.5, right? So this is just making the probability of type 1 error. Now so again I have different values of this particular probability for different values of theta belonging to this omega naught. Now when I take a particular value of theta, right, such that this probability is the highest, then the resulting probability or the resulting expression is your level of significance. Okay, and yeah, that would be your level of significance. And when you, and generally in this case you would get an expression, right? So you would get an expression in C or in your parameter. So it would be an expression. It would generally not be a particular value, it would be an expression. And after you calculate your theta observed and you actually put numbers, you plug in the numbers, you get a particular value of this, right? You get a particular value when actual numbers are put in, and that is known as the size of the test. Okay. uh, what the heck? I can't scroll down. Weird. Huh. Anyway, so that is what size of the test is. Okay, just a sec. Just a sec. माँ माँ पानी दीजिएगा थोड़ा. Right. So that is the size of the test, and that is probably it, right? So I really don't want to spend too much time repeating the same thing and repeating the same theory. Rather, I would just do a few sums, and that would be much more helpful. Yeah. So yesterday we did this sum. This is 9.1, right? So yesterday with this question number 1 we did this. Today let's do a few more. So let's do question number 2. And this says ki suppose x1, x2, xn is a random sample from a uniform distribution in 0 theta, and the following hypothesis is to be tested, right? So I want to see if theta belongs, if theta is any number which is greater than 2 or if it is anything less than 2. And the test statistic that we need to consider is yn, and yn is just maximum of all these sample values, and the test procedure that is given to us is that we reject h naught if yn is less than 0.5, right? So kind of imagine that you are conducting this study, and this is the question that you want to answer, and on what basis do you answer this? You answer this on this basis, right? Ki what is the value of my maximum value of this random samples? If the maximum value of the random sample happens to be something which is less than 1.5, I would reject my h naught. I would reject the claim that theta is greater than 2. I would reject that claim. But if it is not so, if it turns out that the maximum of these sample values is something which is greater than 1.5, then I would not reject the claim that theta is greater than 2, right? So this is the context that is given to us, and we need to calculate these things. We need to calculate the power function, or we cannot calculate the power function. We need to kind of derive the power function. So we would actually get a power function. We would get a function. We would not get a number. We would get a function, and then we need to determine the size of the test, right? So these are the two things that we need to do. So let's just quickly do this, and again, if at any point this is bit fast, interrupt me. That is okay. So let's say exercise 2. It is given that x1, x2, xn follow a uniform distribution in 0 theta. H naught we need to test is theta is greater than or equals to 2. Alternative hypothesis is theta is less than 2. Test rule, or what we often denote as delta, that is ki yn greater than or equals, sorry, was it greater than or equals to? It was less than or equals to, sorry, right? So right, so if this yn is less than or equals to 1.5, then reject h naught, else except h naught. So this is the rule that we follow, where what is yn? Yn is just maximum of the sample values, right? Okay. Now we need to, and I would suggest while doing these sums, write everything down, right? So yeah. So while doing the sums, I would suggest write everything down, and that would just make everything more clear. So we need to calculate the power function, right? So power function. Now what is power function? Power function is just sum this delta, and it is just probability of rejecting h naught, right? So write it down. There is no harm in writing it down for a few times. So this is it. Now what is probability of rejecting h naught? Probability of reject, so when will we reject h naught? When yn is less than 1.5, right? So when yn is less than or equals to 1.5, and to calculate this probability we need some value of theta, right? So we assume that to be theta. Now we have two cases. One case is theta is greater than or equals to 2, or if it is less than 2. Okay, right. Huh. So in general, if let's say if x1, x2 and xn follow a normal a uniform 0 theta distribution, then, and if yn is defined as the maximum of x1 to xn, then the probability that yn is less than some value, let's say a, is what? Less than or equals to some value is basically probability that x1 was less than or equals to that value times probability of x2 was less than or equals to that value, and so on till probability of xn was less than or equals to that value, right? Because so if the maximum value is less than a, then each of these values must be less than or equals to a, right? And we know what these probabilities are. We know that we have a formula for the CDF of the uniform distribution, and it is just the value that we are talking about minus the lower limit, right? So the lower limit here is 0 divided by upper limit minus lower limit. So upper limit is theta, lower limit is 0, right? Right. And this would just turn out to be just a by theta, right? So and for each of these we have a by theta, a by theta, a by theta. So ultimately it turns out to be a by theta to the power n, because we have n terms here. So this is the general case. So what happens here, we just have 1.5 by theta to the power n. Now there is a bit, so this needs to be, this requires some thinking. So okay, so till this much is fine, but think okay, yeah, I guess this is it, or do we need to do something else? I guess this is the power function, but I mean there is one more thing that we can, okay, just हाँ बोल तुषार.
अरे लास्ट क्लास में मैं नहीं था ना, तो तुम लोगों ने ये कवर किया कि पावर फंक्शन के ग्राफ से टाइप 1 टाइप 2 एरर कैसे निकालते हैं, या फिर इफ इट इज गिवन दैट इट इज अ बाइनोमियल तो उसका पावर फंक्शन स्केच कैसे करना है?
No, we have not discussed it, we can discuss it today.
ठीक है.
Okay, so this is what I think is the answer. I'm not sure. And okay, so one more layer of complication that we can add. So this is the power function, right? So this is the power function, that pi of theta given our test procedure is this. But this is if theta is greater than or equals to 1.5. If it is less than 1.5, then this probability would just be 0. Wait, would it be 0? Okay, just a sec. No, 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 no. It won't be. If it's 0, then okay, no, sorry. I guess this is it. This is the answer. Forget this. Now let's just recheck this, because I'm not really confident if this is the final answer, because I think Sumit had sent me this question and this was not so simple. Just a sec. Just a second. Chapter 8. But it's still 8. Chapter 9. Right. Oh no, this Ochana. So there is a bit. Okay, got it, got it, got it. Right. So this should be 1. Yeah, I was kind of right. So yeah, so was this clear to everyone कि ये कैसे आया?
हाँ.
Okay.
Yes.
So I mean, instead of saying कि हाँ clear था, just someone please just interrupt me if you don't understand. ठीक है, because so if you actually look at the answer, and this is what I was missing, if you actually look at the answer, they have done just one more thing, is that see, if theta is greater than 1 point, so what is this theta, right? So this is your any let's say uniform distribution, right? Let's say this is 0 theta and this is 1 by theta. This is your density of this, and this is how your uniform distribution looks. Now if your actual theta is here and you draw samples from this distribution, it is impossible to get a value that is here, right? Because you are drawing a sample from this distribution, so you can't get a value which is beyond theta. And similarly, you are always guaranteed to get a value which is to the left of theta, right? You are always guaranteed that. So the let's say x follows a uniform distribution between 0 comma 4. The probability of x being less than or equals to 4 is 1, because you'll always get a value of x. If it is actually drawn from this distribution, the value of x will always be less than 4, always. So the probability of this is 1. So what they have done here is they have kind of did two things. They have said ki, okay, if theta is greater than 1.5, then no issues, but if theta is less than 1.5, right, our maximum value will always be less than 1.5, because in this case the upper limit is 1.5, or it is something which is less than 1.5. So we'll always get any value that would be less than 1.5. So that probability is just 1. And if theta is greater than 1.5, then we have this thing. But if it is less than 1.5, then we have this thing. So I hope this was clear. And now if you want to plot it, it's really easy to plot it. Easy, I don't know if it is easy. So this is your power function, and this is your parameter thing, and this is where something happens, right? So this is 1.5. Let's say this is 1. So till 1.5 we have a straight line, so the value of the power function is just 1, and then it starts to decline, right? Because as the theta increases, this ratio falls, right? And it starts from 1. So when theta is equals to 1.5, this thing is actually 1, and then it falls. So after this point, it will just start to fall. So this is the plot of the power function. Let's do one more. I want to do a good number of things. Oh, and we had another question. What is the size of the test? Right. So right. So what is the size of the test? The size of the test is, to get the size of the test, we need to calculate the maximum significance level, and right. So we need to calculate the significance thing, and that is just maximum of this power function when my theta is in your theta naught, right? So my h naught is correct, but I reject it. What's the probability of that happening? Now this is equivalent to maximum of this probability of yn being less than or equals to 1.5 when my theta belongs to this set, right? When my theta is in this set, that means my theta is greater than or equals to 2. So it is in this set, right? And we just calculated this. So this is maximum of theta is in this set, and this expression right here is just 1.5 by theta to the power n, right? And why aren't we using 1? Because theta, so it is 1 only if theta is less than 1.5, but we are only considering all those thetas which is in my, which is specified under my null, so which is from 2 to infinity. Now we need the maximum of this thing, right? So we want that particular value of theta such as this expression is maximum. And as you can see from this power function, if you increase the value of theta, this expression's value falls. So for what value is this maximum? Can anyone say that? If I keep increasing my theta's value, this expression keeps falling down. So what is an appropriate value of theta which is in this range such that this expression is the maximum?
2.
Right, 2, right? So this is basically, so what is the maximum of this thing? You just put theta to be 2, so this is what, 3 by 4, right, to the power n, and that's your significance level. Now in this case, your significance level and your size of the test is actually the same thing, because generally when you calculate the significance level you get an expression. Basically the thing is, यहाँ पर बोला हुआ है कि this is when you reject your h naught. If instead of 1.5 you had some general value c, this entire thing would have been a function of c, and then if you actually plug in the value of c, you will get an expression like this, and that would be your size of the test, right? So since we already have that c here, it is already given us to be 1.5. This is exactly what the size means. So this is the size of the test. So this is how you do this one. Let's look at the next one. Okay, so not this one. This is, as I said yesterday, this is a pretty big sum, and this is not difficult sum. It's just you need to look up the binomial table over and over again, and you need to do those things. It's take a look at the solution, but I would suggest don't do this question. It's just lengthy. It's nothing. There is nothing extra going on here. Okay. Let's do question number 4. Question number 4 says, again, x1 to xn is a random sample, normal distribution, mean is unknown, variance is known to be 1. We want to test this hypothesis. Our sample size is given to be 25, and test procedure is that if this thing is greater than or equals to some c, then we reject h naught. Now we need to determine such a c such that the size of the test is 0.05, right? So in this question we were given that c, right? हम लोग को वो c दिया हुआ था. We knew what this c is. In this question we don't know what the c is, and we need to determine such a c such that ultimately whatever be the expression for the size of the test that we get, that should be equals to 0.05. So let's do this. So again, x1, x2, xn. Okay, just a sec. Let me write. This is a recording. This is normal unknown mu and known variance 1, right? We need to test the hypothesis that mu is equals to mu naught. Alternative hypothesis is mu is not equals to mu naught. And my delta, that is the test rule, is reject h naught if mod of xn bar minus mu naught is greater than some value c. What does this mean? This means कि जो proposed mean है और जो observed sample mean है, if the difference or if the distance between those two things is really large, then I say it is less likely to be the case where mu is actually equals to mu naught, and that is why I reject my null hypothesis. So this is what has been given to me. So to calculate the significance level, etc., etc., we always need to calculate this power function, right? So let's just calculate the power function. So power function, again, write everything down. It would just make everything much easier. It is just so power function is a function of my parameter. What is my parameter? My parameter is mu, given my test rule delta. So this is just probability of rejecting h naught, right, given my parameter mu. And if I change this mu, my probability will change. That is why this entire thing is a function of mu. So when do I reject my h naught? I reject my h naught if this mod of xn bar minus mu naught is greater than some c, right? Now what does this mean? This is just 1 minus probability of xn bar minus mu naught being less than c, right, given mu. What does this mean? This means that xn bar, so I am just removing this mod, xn bar lies between mu naught xn bar lies between c distance of mu naught. In other words, this is just c minus mu naught less than xn bar c plus mu naught, given the parameter mu. Now we know the distribution of xn bar. We know how xn bar is distributed. Xn bar, any sample, you take any sample mean, you subtract it with its variance, with its expectation, right? So mu is what? Expectation of So expectation of xn bar is this mu, right? So you subtract its expectation and divide by sigma by root n, not sigma, sigma by root n. So in this case sigma is given to be 1, n is given to be 25, right? So sigma by root n is just 5, 1 by 5. So 5 times xn bar minus mu follows a normal distribution with mean mu and variance 1 by 5. Sorry. Right. So xn bar follows a normal distribution with mean mu and sigma and variance 1 by 5. So xn bar minus mu by 1 by 5 follows a standard normal, that is normal with mean 0 and variance 1, right. So I transform this xn bar to this thing, and then I have the standard normal variable variate in between, and then I can use the CDF of standard normal to get my final answer, right. So that is just 1 minus, I do this C minus, so I need to have what? This should be xn bar minus mu by 1 by 5. So I just do that. I had C minus mu naught here. I subtract mu, I divide by 1 by 5. Same thing I do here. I have C plus mu naught, I subtract mu, divide by 1 by 5. And yeah, so this is what I have. And what else? Mu naught minus mu naught. Anyway, whatever this is C minus mu naught, and I am like doing every step so that it's very clear. I don't think so much step is required in the exam, but anyway, right. And so basically I am writing this thing as a z variable, so z, and I know the distribution function of this. So okay, am I missing something here? Xn bar minus mu is less than sigma is mu naught minus sigma. Right, I did make a mistake. This should have been mu naught minus C, right? So right, someone should have interrupted me. So when we have generally, let's say x minus a is less than b, this generally means that b minus a, sorry, making the same mistake again, a minus b less than x less than a plus b, right. B is the distance, so this should have been mu naught minus c. And this is mu naught plus c. So I have to make the same changes here too. This should be mu naught minus c minus mu, and this should be mu naught minus c minus mu right. So this is my power function, right. So I just write this in terms of the CDF. This is 1 minus phi of this thing, C plus mu naught minus mu by 1 by root 1 by 5 minus the CDF of this thing, mu naught minus c minus mu by 1 by 5. Okay, now the thing is, so this is my power function, right? This is my power function. I needed to find the size of the test. Sorry, I needed to find the value of C such that the size of the test is 0.05. So, right. So what is my significance? Significance of the test. It is the maximum value of this entire thing, maximum value of my power function when h naught is true. Now, in this case, we had a range of values for our parameters. That is why we had to think कि अच्छा क्या हो रहा है? If I put different values of theta, this entire thing goes down, and that is why the appropriate value of theta to maximize this thing should be 2. But in this case, that is much easier, because in this case we just have a single value under our h naught. So we do not have a range of values. So under h naught there is only one value, and we can have only one value there to maximize the function, because there is no other value to put in, right? So the significance of the test is just nothing. It's let's denote it by alpha delta. It's just 1 minus, and wherever I have mu, I just put mu naught, right? So if I do that, I have what, phi of c by, or just 5c, right? 5 will ऊपर आ जाएगा, and I have phi of minus 5c, right? Now I kind of use the symmetry of normal distribution. Now if I have, let's say, a value here, so, or let's say if I have a value here, let's say this is minus a, so this is 0, this is minus a, and this value is such that to the left of this value I have, let's say, some percent of area, then minus of this value, which is a, will have the same amount of area to its right. This is what the symmetry tells us, right? So again, notice that this is in the same form, right? So I have a positive value here, and then I have a negative value here. So I know the area to the right of this is the same as the area to the left of this. Right. And so I can just rewrite that. So what is area to the right of this? Area to the right of, okay, or am I complicating things? I think I am complicating things. So area to the, so this thing, right? So this thing denotes this. Okay, so let's use different colors. So this thing right here represents this area, right? And this thing here represents this entire area. So when we subtract that, essentially what we want the area in between, right? So we want this area. So these two things together essentially translate to this yellow area, right? Now what I can do is, so what I can do is I can just take this area, I forget about this thing, I just take this area, I multiply it by 2, because I have to calculate, because I have to take into account this area too. So I take this area, I multiply it by 2, and then I subtract with 1. So I'll get this yellow area. And that is what we can do. I can just, I just take this probability or this area, I multiply that by 2, and then I subtract by 1. Doing that will get what? 1 minus 2 phi of minus 5c plus 1, which is weird. Maybe it is not, who knows. So this gives us, huh,
I think it should be 1 minus 2 times pi of minus 5c.
right, sorry, right, because this is always less than 1, right? So yeah, thank you. कभी कभी नहीं करता है काम दिमाग. Yeah, so this is just 1 minus 2 times phi of minus 5c, and now if yeah, now it makes sense. Now if you do it, you just have this, right? 1 1 cancel out. Now the question says that I need to pick this c such that this value is equals to 0.05. So according to problem, my size of the test should be 0.05, which implies that 2 times phi of minus 5c should be equals to 0.05. Now it's just a matter of simple algebra. 5 of minus 5c should be equals to 0.025, right, or right, and phi and c is then phi inverse of 0.025 divided by minus 5c, minus 5, sorry. And actually this the thing on the numerator, if you actually look up the value from a table of normal distribution, that would be negative. Okay, so this negative will essentially cancel out, and this c would actually turn out to be something that is positive. So this is the answer that you get. And so this is it, right? So I really wish I could have um, discussed more of these sums, but if we do that, we won't be able to discuss 9.2. So I'll leave the rest to you guys, and I mean, solve a few of this. It's not too difficult. Some of them would require thinking, but it's okay. It's doable. करा जा सकता है. I would really want. Yeah, I would. No. I don't think I would. This is something. It's this question number 12 is a nice question, but I don't think um, it would be asked. If you want to do it, you can do it, but essentially this requires a bit of integration. So if you remember your class 12 integration really well, then this question should be fun. Otherwise, yeah. But this is also the same thing, right? So yeah, so a lot of this question actually asks you to show that the power function is an increasing function or it's a decreasing function. There again you have to make the same thing. You actually have to do the same thing. You, for instance, you have to just calculate the power function, right? And to actually show that something is increasing or decreasing function, that can be done just by observation, right? So for here we can just look at this expression and say that okay, this is a decreasing function of theta, right? So in questions like that, you don't have to do anything else. You just have to derive the power function. So entire 9.1 can be decomposed into three things: calculate, derive the power function, derive the significance level or the size of the test, or find the critical value such that the size of the test is something else. And 90 or let's say 80% of the chapter 9.1 is just that. Is there any specific doubt from 9.1 that anyone has? So now would be a good time to ask. I guess not.
It's not from 9.1, but from ma'am's slides. वही के ma'am has given some power function का graph and she is like, what is the probability of type 1 test and type 2 test ऐसा. Can you infer that using that graph only? आई डोंट थिंक कि वो टेस्ट में आएगा, बट इट्स मैम तो शायद दे दे.
If you have, can you send it to me on WhatsApp?
गिव मी अ सेकंड.
माँ, मेरे को एक बोतल में पानी ला के दे दीजिए ना. Okay, so is there, so बस एक ही स्लाइड है क्या इसके बारे में?
मतलब हाँ एक ही है.
तो I'll look into this and then I'll try to answer this. I mean, looking at the graph and saying ki what is going to be the type 1 and type 2 error is not too difficult. You just have to kind of think thoda sa. So I'm just
The second question was uh, even it was in the slides that what will be the impact, क्या कहते हैं, if the mean or the variance are changed in a normal distribution, so what will be the impact on power function? I think it's in the slide or maybe in the book. I don't remember, but I was kind of confused.
hmm. So okay, so that kind of a question can be answered uh, looking at the expression for the power function, right? So I'm guessing. I'm okay. I'm guessing. I'm not really sure. So when you get a expression for the power function, you can see कि अगर ये बढ़ाने से क्या change हो सकता है, right की तरफ shift होगा, left की तरफ shift होगा, something like that. But I'll look at the slides and I'll try to get back to you. I don't want to say anything wrong at this point, so I'll look into that. But in general, if you want to, let's say, just calculate the probability of type 1 error or type 2 error, looking at the power function, you just, so let's say this is the thing, right? Now, what was the hypothesis here? Here the hypothesis was, let's say, mu is equals to mu naught, and xn bar is this. So यहाँ पर I mean you can kind of suppose your mu naught was 4. Alright, I'll look this up properly and then I'll get back to you. I don't want to confuse myself and you guys too. Let's just, that is a good question, I'll look into it. Coming to 9.2. Again, 9.2 I really don't want to spend too much time on the theory because you guys have heard the theory in class, you guys have heard the theory, you have done it yourselves. I have no doubt that you guys have a problem in theories. Theory is just that. We'll do a few examples and then our life would be a whole lot easier if we just do a few examples. So what this 9.2 deals with is the trade-off that we discussed earlier, right? There is going to be a trade-off in the two types of error, type 1 and type 2 error. You increase your type 1 error, you decrease your type 2 error, you decrease your type 1 error, you increase your type 2 error. So there is a clear trade-off between these two things, and you need to strike some balance between them. Now, this entire chapter says that you cannot minimize both of them simultaneously. You cannot minimize this and that. What you can do is, so it basically gives us two propositions or two results. First result says, okay, yeah, okay, I can add pages here. Weird. Anyway, so in 9.2 what it basically says that so point 1 we can't minimize type 1 and type 2 error simultaneously, right? We can however minimize a linear combination of type 1 and 2 errors, right? What does this mean? I can, let's say, so we generally denote type 1 error to be alpha and type 2 error to be beta, right? So what it says is that fine, I cannot minimize alpha and beta simultaneously. I cannot do that. Unfortunately, I cannot do that. What I can do is I can, let's say, a times alpha plus b times beta, this thing, let's say this is my total error, let's say there is nothing called as total error, but let's say this is my total error. I can minimize this, I can minimize my total error, and yeah, that is something that I can do. And then comes in the Neyman-Pearson lemma, which says that, which kind of says the same thing but in a different manner, is that if we fix either alpha or beta, we can minimize the other. So these three things are basically the highlight of this entire chapter, and that is it. You cannot minimize both of them simultaneously. You can minimize a linear combination of them. You go a step further. If you fix alpha or beta, you say कि अच्छा ठीक है, type 1 error का जो probability है वो 5% से ज़्यादा नहीं होना चाहिए. So you fix it at 5%. Then you can minimize beta accordingly. So you can have a test which has a maximum type 1 error probability of type 1 error of 5%, and corresponding to that, whatever minimum type 2 error that you can achieve. So you can find a test like that. That is basically the Neyman-Pearson lemma, which is NP lemma. Like, so yeah, so result 1 says कि if you want to do this, right, if you want to minimize a linear combination of these two errors, what should you do? So results 1 says that if, right, so okay, so ha, right, so if let's say this is your h naught and this is your alternative hypothesis, and under your h naught, let's say under h naught, your hypothesis states that some probability distribution f is basically equals to f naught of x. Okay. And under alternative hypothesis you say that it is not f naught of f naught of x, it is f1 of x. Okay, it is not a good idea to use this notation. Wait, what did they use in the book? Just a sec. Okay, sorry. Yeah. So under h naught of x, you say that your theta is equals to theta naught. Under alternative, you say your theta is equals to theta 1. If this is your hypothesis, and if you want to minimize a linear combination of the type 1 and type 2 error. So result 1 says that if we reject h naught, when f1 of x divided by f naught of x is greater than a by b, then we minimize alpha time just a second. Right, so if we do this, so at this point we are more interested, so in earlier chapter in 9.1 we were more interested in calculating the power function and errors. We didn't really care too much about finding the best C, right? So we kind of answered questions like कि कौन सा C होने से the type 1 error is going to be something, type 2 error is going to be something, but we only cared about one error at a time. In this section we are essentially more worried about both the errors simultaneously, and we want to get a test rule. Now what's a test rule? Or we want to kind of find that C, right? We want to find that C such that this linear combination of error is minimized. So that is what we deal with in this section, right? So result 1 says कि अगर हम अपना h naught को reject करते हैं, अगर f1 है whatever this is, अगर ये होता है, अगर हम तब h naught करेंगे, then we minimize this thing, some constant a times our type 1 error plus some constant b times our type 2 error. Now what is f1 and f naught? f1 is basically your likelihood function of whatever random variable that we have or whatever sample that we have. So likelihood function of the sample under h1, and f naught is just the likelihood function of the sample under h naught, right? So this is all that this result says. तो मतलब क्वेश्चन में पूछ लेगा कि which test would minimize this 3 times alpha plus 4 times beta, then you would have to kind of use this कि according to this result, if we reject our h naught when f1 of x by f2 of x, f1 of x divided by f naught of x, when this is a by b, यहाँ पर a 3 है, b 4 है, right? So 3 by 4, then this linear combination of errors would be minimized. And then what you need to do is यहाँ पर कुछ एक expression आएगा, you need to solve that expression or you need to simplify that expression, and you will get a simplified thing, and that would be your answer. Nothing too much. So this was one of the results. The other important result that we have is the Neyman-Pearson lemma, which says, so result 2.
Yash,
Huh,
so we already have a value of A and B.
yeah, we already have a value of A and B.
Okay, okay. We don't need to calculate it, right?
We don't need to calculate it. Either 3 4 या 1 3 कुछ ऐसा दिया हुआ रहेगा, या फिर it would be some general value a b, तो आंसर भी वैसे जनरल a b के टर्म्स में आया, बट कैलकुलेट नहीं करना होगा.
Okay, okay.
Result 2 says that what did result 2 say? I forgot. कि if we reject h naught when f1 of x by f naught of x is greater than some 1 by k, then our okay, I forgot the Neyman-Pearson lemma. Sorry. Ha ha ha. This is 9.3, 9.2 कहाँ गया? Right, so this is the Neyman-Pearson lemma. Suppose that is a procedure that, yeah, so it says that if we do not reject our h naught, if this, so okay, in other words, if h naught is rejected, if this happens, right, or in other words, if f1 by x by f naught of x is greater than some k, then there is no other test procedure such that you could do better in terms of type 1 error, or so basically if you follow this particular test procedure, then if your type 1 error is less than some specified amount, that is something that you have specified, then you must be doing worse in terms of your type 2 error, and the same thing holds the other way around too. So in some sense this is basically a specific case of your first result, right? यहाँ पर basically we said कि अगर we do this then this is minimized. यहाँ पर we are saying कि if you fix your type 1 error, ठीक है, and then if you follow this rule, then the only way that you could kind of do better in minimizing your type 1 error is if you compensate for it in terms of your type 2 error. So again the same trade off thing happens, and essentially what this means is कि if you do this, then for a fixed type 1 error, type 1 or type 2, so this holds both way, right? So if you follow this test procedure, then for some fixed type 1 error, type 2 error or type 1 error is minimized. This is what this says.
Yash, I think it should be k, not 1 by k.
Same thing.
About
Same thing. I mean, इसको 1 by k को you take this as, let's say, m, same thing, doesn't really matter.
okay.
K 1 by
Okay.
k. So fine, let's write it k. Actually, it's better to write it as k because then the calculations are easier. Sorry, it's better to write it as just k, and the calculations are easier. So again, I just threw a lot of theory at you. You might not have understood it. There is no point also. I mean, there is obviously point in understanding theory, but what I'm trying to say is let's do a few examples and then it would be a whole lot better. So let's just do one. Right. So take a look at this question. This question says that f naught x be a Bernoulli distribution with parameter 0.3. F1 is Bernoulli distribution with parameter 0.6. Now suppose that a single observation x is taken from a distribution for which the PDF is either this or this, and the following sample or the following hypothesis is to be tested कि h naught is कि इस पर्टिकुलर डिस्ट्रीब्यूशन से हम ड्रॉ किए हैं, अल्टरनेटिव हाइपोथेसिस कि हम दूसरा डिस्ट्रीब्यूशन से ड्रॉ किए हैं, एंड आई वांट टू कम अप with a test procedure such that this linear combination is minimum, right? So यहाँ पर a और b का वैल्यू क्या है, यहाँ पर a और b का वैल्यू जस्ट 1 and 1 है, right? So this is 1 times this, 1 times this, and so यहाँ पर they generally write type 1 errors as alpha of delta. This basically means कि type 1 error क्या होगा if I consider some particular test rule delta. So if you change your test rule, obviously your type 1 and type 2 error will change. That is why they write it as a function of your test rule. So this is my question. This is so h naught is f1 of f naught of x, f of x is just f naught of x, and h1 is f of x is equals to f1 of x, right? And you take a single observation from a Bernoulli distribution with parameter p, and if your h naught is true, then this parameter p is 0.3, and if your h1 is correct, then your parameter p is 0.6. Now we need to minimize alpha plus beta. This is the linear combination that we need to minimize. So the test rule that would minimize alpha plus beta is if we reject h naught when what does my first result say, when f1 of x by f naught of x should be greater than a by b. यहाँ पर a भी 1 है, b भी 1 है, so it should be greater than 1, or f1 of x is greater than f naught of x, right? Now what is f1 of x? f1 of x is the likelihood function of my sample. Now I don't really have a sample here. I have a sample, but the sample size is 1 because I am only drawing a single Bernoulli variable, right? So this likelihood function is just the probability of observing what I observe, right? So x is a Bernoulli p, right? So what is so x can take two particular values, 1 and 0, right? Now or so it can take a probability, it can take 1 with probability p, right? Or it can take 0 with probability 1 minus p, right? So this is kind of the PDF or sorry PF of Bernoulli distribution, right? So this is where I am getting. So अगर x का value 1 है, so this entire thing would be 0. I would get just p. What is p? P is just the probability of observing 1. अगर x का वैल्यू 0 है तो ये सॉरी यहाँ पर एक x होना चाहिए था, सॉरी. अगर x का वैल्यू 0 है तो this entire thing would be 1. Sorry, this would not be 0, this would be 1. But if the value of p x is 1, x is 0, then this p would be 1 and this entire thing would be what we have, right? So this. Now यहाँ पर we have specified कि f1 में p का वैल्यू क्या है, f2 में p का, f0 में p का वैल्यू क्या है. So what we have is this. So under f1 what is it was under f1 0.6, right? So this is 0.6 to the power x and this is 0.4, 1 minus 0.6 to the power 1 minus x. This is greater than the same thing for f0, 0.3 to the power x, 0.7, 1 minus 0.3, 0.7, 1 minus x. Now when will this condition hold, right? So this condition will only hold when x is equals to 1, right? Because if x is equals to 1, this entire thing is just 1 and this entire thing is just equals to 1, and you have 0.6 greater than 0.3, which is true. So this implies कि ये condition तभी hold करेगा when x is equals to 1. If x is equals to 0, the opposite is going to happen. We don't want the opposite, we want this. What does that mean? It means कि we minimize alpha plus beta, where alpha is my type 1 error, beta is my type 2 error, when, or we minimize this if we reject h0 if x is equals to 1. Right? So I draw a sample. If that sample turns out to be a 1, I reject my h0. If that sample turns out to be 0, I don't reject my h0. Was this clear?
Yes.
Okay. This is Q1. Let's do a tricky one. Defined as follows. This is minimum, that is defined as follows. Okay, this 2 is pretty simple. We will do this and then I'll leave 3, 4 to you because वो करने से तुम लोग का भी clarity आएगा, and then I'll do something which is really tricky. So let's just do question number 2 first. So 2 says कि I have two PDFs, f0 and f1x, and they are defined as this, right? And I need to test this hypothesis such that this particular linear combination is minimum, and then I also have to find the value of this, the minimum value of this. So let's just do this. This is question number 3. That's question number 2. Right. हाँ. क्या था कि h0 is f of x equals to f0 of x, h1 is f of x is equals to f1 of x. And by the way, if any one of you have like a specific doubt in this exercise, let me know. तो फिर हम वो करेंगे, कोई दिक्कत नहीं है. Where need to minimize alpha of delta plus 2 beta of delta. F naught of x is what? It is 1 and 0 when x lies between 0 and 1, and this is otherwise. F1 of x is 2 of x0, it lies between this. Then right. So again, very straightforward question. What is A here? A is 1, B is 2. So to minimize this particular linear combination of type 1 and type 2 errors, we need to reject H naught if f1 of x by f naught of x is greater than a by b, 1 by 2, right. So a is equals to 1, b is equals to 2 here. Yes, this is recording, I hope. So right. So this. Now what is this? So see, when x lies between 0 and 1, I know what this is. If it doesn't lie in this range, then this is just 0 by 0. So that doesn't make any sense, right? So we just consider this 0 to 1 wala case. In 0 to 1, f1 of x is just 2x. So this is just 2x, and denominator is just 1. That is greater than half, which implies x should be greater than 1 by 4, which means to minimize this particular linear combination of errors, I need to reject, or we need to reject H naught if the observed x, whatever that we observe, is greater than 1 by 4. So if we observe a value of x which is, let's say, 1, I reject my H naught. If it is, let's say, 0.1, then we do not reject H naught. So this answers our first question. What should be our test hypothesis or test rule to minimize this? Then we had to calculate the minimum value of this, right. So the minimum value of this would be value of type 1 error and type 2 error if we followed this test rule, right. So this is our test rule now, and this test rule will minimize this. So what is my alpha delta? So alpha delta is basically probability of rejecting H naught when H naught is true. Now when do we reject H naught? We reject H naught when x is greater than 1 by 4. And what does it mean when we say that H naught is true? H naught is true, it means the PDF or PDF of x is given by f naught of x, right. So f of x is just f naught of x. So according to f naught of x, this probability is what? 1 by 4 to 1 f of x dx, right, because beyond 1 the probability is, or the density is just 0. So we don't write that here, which means this is 1 by 4 to 1, f naught of x is just 1, right. So this is just dx, which means this is just 1 minus 1 by 4, so this is just 3 by 4. So this is my alpha delta. Q2. Then I need to find my beta, right. So what is beta delta? It is just probability of accepting H naught when H naught was false, right. So when do we accept h naught? When x is less than 1 by 4, because if it is greater than 1 by 4 we reject h naught. So when do we accept it? When it is less than 1 by 4. And what does it mean when we say h naught was false? It means that h1 was correct, which is f of x is basically given by f1 of x, and this probability is what? 0 to 1 by 4 2x dx, right? Because if it is anything which is less than 0, it is 0. If it is anything, yeah, that is it. So this is what? 2x square by 2, 0 to 1 by 4, 2 cancels out, you have this. So this is just 1 by 16. So the minimum value of alpha delta plus 2 times beta delta, alpha delta we found out to be 3 by 4, and this is 1 by 8. So I can write this as 6 by 8, right? Plus 1 by 8 is just 7 by 8. This is my answer. So a few of this, at least starting ke taraf mein jo questions are, they are like very easy. So you do the same thing and you get the answer. Like question number 3 also you do the same thing, right? So again, determine the procedure, determine the minimum value of this. Same thing. You guys should try this. Question number 4 is again the same, right? Here, okay, so
यश
हाँ,
इसमें हमने लाइक्लीहुड फंक्शन क्यों नहीं बनाया?
because good question. Because as follows, suppose, yeah. So the reason why we did not make the likelihood function, actually we did make the likelihood function, we implicitly made it. Why? Because we have a single observation of x. So what is the likelihood function? Likelihood function of, let's say, f1 is basically, so if we have, let's say, x1 x2 ऐसा करके sample size is n and this is my sample, then likelihood function is basically, if we are, let's say, calculating the likelihood function under f1, it should be f1 x1 takes this particular value x1 times f1 x1 x2 takes this particular value x2 and so on. And यहाँ पर we would have gotten 2 times x1 times 2 times x2 times 2 times xn. It would have given us 2 to the power n. This entire thing, we multiply this entire exercise. This is what we would have gotten if we had a n sample case, but we only have one single observation here, right? So we don't have this, and we don't have this dot dot dot. We have none of this. We have none of this because we are taking only a single observation, and we are just left with 2x1. That is why it seems like we are not making the likelihood function, but we are making the likelihood function. It's just there is only a single observation. And this is a really good question because, let's say, in this particular exercise, okay, let's do this right now. In this particular exercise, we have to kind of construct the likelihood function because now we have a n sample, the sample size is n. So we actually have to construct the entire likelihood function and we have to do it. So let's just do this, right? So I was so now is that, by the way, clear? Why didn't we do the likelihood thing?
Yes.
Okay. So yeah, in this question number 4, they have said that we need to find a test procedure such that alpha is less than 0.1 and beta is minimum. Right, and this is where the second result comes into the picture, or the Neyman-Pearson lemma. Try question number 4 by yourself. This is very similar to question number 5. We are going to do the question number 5 now. So after doing question number 5, you guys should be able to do question number 4. So let's look. So see, question number 4, 5, they have said the same thing, except ulta kar diya hai. यहाँ पर they have said that alpha should be less than 0.1. यहाँ पर they are saying that beta should be less than 0.5 and alpha should be minimum. So doesn't really matter. थोड़ा बहुत change होगा, but nothing too big. So x1 xn is a random sample from a normal distribution with mean theta, unknown variance 1. This is the hypothesis that we need to test such that beta is this and alpha is minimum. So this is question number 5, right? So yeah, so x1, so xn, they follow IID normal with unknown mean mu, and this is the variance. We need to test this hypothesis that mu is equals to 3.5. Alternative hypothesis is mu is equals to 5, and need a test procedure, need a delta such that alpha of delta is less than or equals to 0.1 and beta or delta is minimum. So according to, so how would you do this question in exam, right? So in exam, how would you do this? You would start off by mentioning that according to Neyman Pearson lemma, to minimize beta delta such that so to minimize beta delta such that alpha delta is less than or equal to 0.5, we need to reject h naught when f1 of x by f naught of x is greater than some k. We don't know this k. We are going to find that k, right? So earlier cases we knew what this k was, right? Because we knew the exact linear combination that we were minimizing. यहाँ पर we don't know it. So behind the scenes क्या हो रहा है? Behind the scenes actually you are minimizing this. You are minimizing alpha delta k times alpha delta plus 1 times beta delta. You are behind the scenes you are minimizing this, and that is why you are getting this using the first result. But then you are going to do everything and then you are going to get some, okay, let's just do it, and if I do it, it will be much more clearer. So this is how you start. Now what is f1 of x? F1 of x is now a likelihood function, right? So as she mentioned right now we would have to create a likelihood function. So now, so what is basically this? It is basically the f of, let's say, x1 takes this particular value x1, so take this particular x2, take this particular xn. Now this is a normal distribution, right? So this is 1 by sigma root 2 pi e to the power minus half x1 minus mu by sigma squared. This is for all the n cases, right? And if you club things together, you get 1 by sigma 2 pi, and there is no need to actually write this sigma because we know that this sigma is 1. Since I have written it, e to the power minus half, okay, this is just minus half summation of xi minus mu square, right? Because this sigma is 1, I am not writing that here, this is it. And so this is under f1, right? So under f1 this mu is equals to 5. So let's say this is the general f of x. So f1 of x would be the same thing, it would be the same thing but यहाँ पर एक xi minus 5 square होगा. And if you had f naught under h naught, you would have had minus 3.5, right? So this is the two likelihood functions. Now if you put that here, what do we get? We if you divide this, this constant thing is going to cancel off, and you will essentially end up with e to the power minus half summation xi minus 5 squared. Denominator में you have e to the power minus half this, right? So if you take that to the numerator, this will turn into a plus, and you have a plus e to the power xi minus 3.5 का square. This is greater than k. Oh, now I can scroll down. Weird. Anyway, so right, so now there is a bit of boring algebra, we can't run away from it. So this is just take the half out, and this is summation xi square plus 25 minus 10 summation xi, right? I am really bad at doing boring algebra, so please pay attention because I might make some mistake here. So please don't let me make any mistakes. So यहाँ पर माइनस समेशन एक्साइज स्क्वायर आना चाहिए, माइनस 3.5 का स्क्वायर क्या होता है? जस्ट अ सेक. 3.5 times 3.5, 12.25. Thank you. 12.25 प्लस, हाँ बाद में ये तो नहीं खाते हम, ठीक है. तो eat it. And this is 7 times summation xi, right? Sorry, 7 times summation xi. This should be greater than k. I hope this is correct. xi is going to cancel out, कुछ cancel out होगा. So ultimately I have e to the power, and ultimately the thing is, ultimately you will find that doing this much of thing is essentially not really of much consequence. But anyway, right, so यहाँ पर summation exercise cancel हो जाएंगे. मेरे पास यहाँ पर 12, so this is 25 minus
यश
हाँ
यश ये 25 n नहीं होगा, क्योंकि कोई भी अगर हम कांस्टेंट में समेशन लगाते तो वो n a हो जाता है, लाइक समेशन a इज इक्वल्स टू n a.
राइट, देखा, यही बोल रहे थे, गलती कर सकते हैं हम. वेरी गुड. Yeah, so that should be an n here. Right. Now what? Yeah. Now the ये सब cancel हो जाएगा. I should have 12.75 here, right? Calculate, एक second. I don't want to take chances. What is 12.25 minus 25? 12.75, right? So I have minus half 12.75 n minus 3 summation xi, right? 3 summation xi, and that is greater than k. Now I take natural log on both sides, so I get minus half of 12.75 n minus 3 summation xi greater than natural log of k so this is 3 by 2 summation xi or this is 3n by 2 x bar, right? So I am dividing by n, multiplying by n. So this becomes x bar, sample mean. What is 12.75 by 2? 6.375. I take that here. So natural log of k plus 6.375. Or x bar should be greater than 2 times natural log of k plus 6.375 whole divided by 3n, and this is my test rule, right? Let's say this is some k prime. So point being that if I do this, if I reject my h naught, if my sample mean is greater than this k prime, then this particular linear combination is minimized. But I also need to have this alpha of delta to be less than 0.1, right? So I need to choose that k prime accordingly. So what I do is I explicitly calculate my this, which is probability of rejecting h naught, and my mean is 3.5 because under h naught mean is 3.5. And now when do I reject h naught? I reject h naught when x bar is greater than this k prime, right? So when xn bar, this is xn bar, or fine, no need to write xn bar, x bar is greater than k prime given mu is equals to 3.5. Now x bar has its own, x bar follows normal distribution, right? So x bar follows normal distribution with mean mu and variance sigma square by n, right? Sigma square is given to be 1. So this follows basically this. So we transform this. So x bar minus, तो mu के जगह क्या माइनस करेंगे? 3.5 माइनस करेंगे because mu is given to be 3.5 under h naught, and we would divide this by 1 by n. This should be greater than k prime. We have to do the same thing here also. This basically gives 1 minus phi of, so now this is a z distribution, a z variate, right? So this is, I can just write this as 1 minus phi of k prime minus 3.5 by 1 by n, and according to my question this should be less than or equals to 0.1. So whatever this is, this should be less than or equals to 0.1. So we cannot work with an inequality. So what we do is we just fix this to be 0.1, and now I calculate what this particular value of k prime is. So now it is 0.9 equals to phi of k prime minus 3.5 by 1 by n. This basically means that k prime minus 3.5 by 1 by n is equals to phi inverse of 0.9, which implies that k prime should be 1 by n phi inverse of 0.9 plus 3.5. So this is my final answer. This basically says, so what did we do actually? We used the Neyman-Pearson lemma to minimize a general linear combination of the two errors. A general. So this is some k and this is some, yeah, for some जनरल लीनियर कॉम्बिनेशन को हम मिनिमाइज कर रहे हैं. तो इस कोई भी एक जनरल लीनियर कॉम्बिनेशन को मिनिमाइज करने के लिए मेरा जो टेस्ट होना चाहिए उसका ऐसा एक फॉर्म होना चाहिए, राइट, वेयर आई रिजेक्ट माई एच नॉट व्हेन माई सैम्पल मीन इज ग्रेटर देन सम कांस्टेंट. नाउ आई नीड टू पिक दिस कांस्टेंट वेरी केयरफुली. नाउ एट दिस स्टेज व्हाट डू आई नो? एट दिस स्टेज आई नो दैट वट एवर के प्राइम आई पिक, ठीक है, वट एवर के प्राइम आई पिक for a given level of significance, the other error is minimized. That I know for sure. Why do I know it for sure? Because of the Neyman-Pearson lemma, right? So at that state I only know that कि बस इतना ही पता है कि अगर हम ऐसा, मेरा टेस्ट का अगर कुछ एक ऐसा जनरल फॉर्म होता है तो significance level, for a fixed significance level or for a fixed alpha or for a fixed beta, the other error is minimized. I just know this much. Now I need one more thing. I need my alpha to be at most 0.1. So I need one more thing. So what I do, I explicitly calculate this alpha, the expression for alpha, and I set that equals to 0.1. And then I back calculate what my k prime should be, and that turns out to be this thing. So when I finally write my test rule, so test rule is reject h naught if x bar is greater than this 1 by n phi inverse of 0.9 plus 3.5. If this is my test rule, then two things happen. One, alpha is 0.1, and the second thing is beta is minimum, and that is what they have asked in the question. And this is a very mechanical thing. Every question you need to do the same thing over and over again, right? And why at this point I was saying कि इतना calculation is going to be inconsequential. Why? Because देख यहाँ पर इतना सब करके I get this expression, right? I get this expression. I never really, sorry, I get this expression. I never really use that expression. Whatever यहाँ पर कुछ भी आए उसको हम k prime पकड़ लेंगे, and then I'm going to reject. So what I'm actually trying to say is that instead of doing this, had you just done this much, कि probability of rejecting h naught given mu equals to 3.5, right? So this is basically your type 1 error. And यहाँ पर instead of doing all this, instead of doing just that, if you would have just started with the thing कि we reject h naught if our xn bar is greater than some c given mu equal to 3.5, and this probability of type 1 error should have been 0.1, then also ये c का value we would have gotten the same thing, right? So half of the sum is actually not even needed, but you would have to do it क्योंकि करना पड़ेगा. I don't think you can skip all of this, but point being कि अगर नहीं भी करोगे तो essentially it doesn't matter. Yeah, that's बस वही था. Now so this is question number 5. Same way, sorry, yeah, so this was, oh shit. Okay, so basically I solved this entire question for alpha equals to 0.1, which was not asked in the question. Question में बोला था कि बीटा को 0.05 में fix करना है. I actually had this in mind and I did question number 5. But again, it shouldn't matter, right? So if you actually want to do this, what you would do, you would just calculate the beta. What is beta? Beta is probability of accepting h naught when h naught is h1 is true, right? So when you would accept h naught, when your xn bar is less than this k prime. So this is probability of xn bar being less than some k prime given mu is equals to 5, because now h1 is true. Again you transform it like this and वापस से कुछ एक xn कुछ एक k bar मिलेगा, k prime मिलेगा, and that would be your answer there. So essentially nothing changes. And that is what you have to do in question number 4, in question number 5. In question number 6, if you read this carefully, same thing. ये मेरा h naught है, I need to minimize this, right? And don't really bother कि it minimum rejects this and this. You just apply the Neyman-Pearson lemma. ये अपने आप मिल जाएगा, ये अपने आप prove हो जाएगा, right? And then we have to find that particular value of that constant c. Same thing you have to do here. Instead, so question number 5 and question number 7 are similar in the sense कि यहाँ पर normal distribution में mean नहीं पता था, variance पता था. यहाँ पर उल्टा कर दिया है, यहाँ पर variance नहीं पता है, mean पता है. Same thing. It's just when we don't know mean, we use the t distribution or the z distribution. यहाँ पर since we do not know since this is something that we are testing for, यहाँ पर chi-square distribution use करना पड़ेगा. So that is something to look out for, and otherwise everything is the same. You have to do the same thing for question number 8, question number 9, question number 10. Literally every question is just the same thing over and over again, except I guess ये last वाला कुछ question, but otherwise it is just the same. So I guess this should be
यश
हाँ बोल.
यश जो हमने अभी क्वेश्चन करा है उसके बी पार्ट में n is equals to 4 दिया हुआ है.
हाँ, तो n equals to 4 ये जो आया ना, ये
n is equals to 4 तो इसमें z उसके नॉर्मल की जगह t डिस्ट्रीब्यूशन लग जाएगा. जो हम पीडीएफ जो हम वो निकाल रहे हैं लाइक्लीहुड फंक्शन में,
लाइकली t की जगह z, सॉरी z की जगह t. नहीं, क्योंकि यहाँ पर वेरिएंस नोन है, राइट? तो अगर वेरिएंस पता है तो आई डोंट थिंक वी यूज t. डजंट मैटर द सैंपल. देख लेते हैं, क्वेश्चन में देख लेते हैं. आई माइट बी रॉन्ग. क्वेश्चन नंबर 5 किया ना अभी?
हाँ
अच्छा, ये 9.1 है. 9.2 क्वेश्चन नंबर 5. Right, so they are using the z distribution. So see, when would you use t distribution? T distribution is used when you do not know the variance, right? So अगर variance पता है तो you would never use t, you would use z no matter the sample size. हाँ,
ओके.
अगर variance नहीं पता है और सैंपल साइज 30 से कम है, देन यूज
फिर टी लेना पड़ेगा.
हाँ, बट अगर वेरिएंस नहीं पता है बट सैंपल साइज इज बिग इनफ, मोर देन 30, देन इट इज सेफ टू से कि z से भी काम चला सकते हैं.
हाँ, ठीक है.
तो वही है, एंड लिटरली एवरी अदर क्वेश्चन इज द सेम थिंग. सो
तो फिर उसमें जो लाइक्लीहुड फंक्शन होगा, मतलब जो हम बनाए उसमें फिर टी डिस्ट्रीब्यूशंस वाले लेने पड़ेंगे ना, या मैं एक मिनट, जो हमने n is equals to 4 वाला है, अगर इसमें वेरिएंस भी अननोन होता तो लाइक्लीहुड फंक्शन तो नॉर्मल के हिसाब से ही बनता ना ये वाला.
हाँ, लाइक्लीहुड, क्योंकि देख लाइक्लीहुड फंक्शन किसके बेसिस में बन रहा है? लाइक्लीहुड फंक्शन बन रहा है ऑन द बेसिस ऑफ द सैंपल. सैंपल तो नॉर्मल डिस्ट्रीब्यूशन फॉलो कर रहा है, सो लाइक्लीहुड फंक्शन नॉर्मल के बेसिस में बनेगा.
ठीक.
ये जब हम लोग ये कैलकुलेट कर रहे हैं,
जो हम ये कैलकुलेट, ये नॉर्मल जो टी डिस्ट्रीब्यूशन फॉलो
टी
करेगा।
या नॉर्मल, हाँ टी या जेड
हाँ।
व्हाटएवर। तो
ठीक ठीक।
वही है। और कोई क्वेश्चन किसी का, कुछ भी डाउट वगैरह कुछ भी? नहीं? I don't think so. Okay, I guess